These concepts of permeability and porosity can be a bit difficult to understand. Let's use some basic experiments to help us think about groundwater flow. To start with, we know that groundwater is the result of precipitation infiltrating down into the ground, filling the natural openings that are present in rocks and sand. The type of soil in a particular area largely determines the rate of infiltration. For example, sandy soils allow a high degree of infiltration. Rainwater is very quickly absorbed in sandy areas because they are highly permeable. In other words, they allow easy movement of water. On the opposite extreme, soils high in clay are relatively impermeable, which means they don't allow good infiltration. Therefore, a large percentage of rainwater is lost to runoff and evaporation in areas that have soils like this. Now, once water has infiltrated, what happens to it?
As we now know, groundwater is stored underground in aquifers. The process of adding water to these aquifers is called recharge. The ability of an aquifer to store water is related to its porosity, which means the amount of open space or percentage of void space in the material of the underground rock.
Primary porosity is the void space that originated when rocks were first formed back in geological history.
When we look through a microscope at a sample of porous rock, we can see the tiny spaces between the rock particles. In the same way water fills up the spaces within the sponge, we can imagine how water is able to fill up the void space between the particles of porous rock.
Secondary porosity is the void space that forms after rock has originally formed. Imagine these two bricks as relatively impermeable rock that has fractured, leaving a space within that fracture. This is another place where water can be stored underground. Now that we understand some key concepts, let's take a look at some of the different underground flow paths which form part of the hydrological cycle, from infiltration to underground storage and flow through to discharge back to the Earth's surface.
Groundwater infiltrates into soils until it reaches an impermeable layer where it is then held within an aquifer. Within unconfined aquifers, groundwater flows based on the slope of the water table, also known as the hydraulic gradient. Simplistically, if the aquifer has a high level of permeability, the rate of the flow is faster than within an aquifer with low permeability if they have the same hydraulic gradient.
In sandy or alluvial aquifers, like in the Cape Flats aquifer, groundwater travels up to several meters per day, while in hard rock aquifers, like here in the Hellsworth Mountains, groundwater may move as slowly as a few meters per year.
Another aspect to consider with regards to groundwater flow is that there are different types of aquifers, unconfined and confined, as well as those that are semi-confined. Generally, if undisturbed, unconfined aquifers will eventually discharge either at a spring, river, or wetland, or back into the sea. In some cases, the water level may reach the surface, causing groundwater flooding. This phenomenon often occurs within the low-lying areas of the Cape Flats. Confined aquifers, by contrast, are under pressure and are generally sandwiched between two layers of impermeable rock. When drilling boreholes into these types of aquifers, water may shoot into the air once the top layer of impermeable rock is pierced. They are called artesian boreholes.